welcome to today's episode. Today, I have liquid nitrogen, and I'm really excited about it. Nitrogen is a diatomic molecule that has very weak intermolecular forces, and so to get it to be a liquid, you have to cool it down a lot. And by a lot, I mean a lot. Like negative 196 Celsius, a lot. That means the nitrogen molecules in this container are over 200 degrees colder than the room that I'm in, which is around 20 degrees Celsius. And that means we can do a lot of really awesome stuff with it. So let's get started. This is a special insulated container called a Dewar Flask, and it's specially made to hold things like liquid nitrogen that are very cold or even very hot, if they're like giant thermoses. Start by taking off the top, and you can see a little bit of the cold fog forming right around there. This is not an airtight situation because some of the nitrogen evaporates over time, and we have to have ways to release the pressure. So it's not screwed on airtight, and we also have a little release valve right over here. If you can see it, it really, at first glance, looks a lot like water. Once the container cools down a little bit around it, the liquid nitrogen settles in and just is doing sort of a mild boiling action right now because the room is about 200 degrees hotter than the liquid nitrogen. I have some nice little yellow flowers from my yard, and I'm gonna go ahead and put those in. Maybe you can hear that. And after only a few seconds, they've cooled down to the point where I can just crush them like that, and they've completely lost their pliability. They've turned brittle instead of, flexible. And now for the good old racquetball trick. That in there. Very nice. And again, you can see some boiling action right around the racquetball because again, the racquetball is 200 degrees hotter, or was, than the liquid nitrogen, and so the nitrogen that's hitting it is feeling that intense heat and is boiling around that racquetball. So after a couple of minutes in the liquid nitrogen, the racquetball is going to come out, and I'm going to attempt to hit it with the hammer. Just like the flowers, the racquetball itself has lost, just like the flowers, the racquetball itself has lost some of its pliability, and it's now brittle, and so when I smash it with the hammer, it just shatters instead of bounces like it did before. Now also, just for fun this week, we made some slime out of polyvinyl alcohol and some borax, sodium borate, and we can see that the slime is really slimy and kind of weird. And if you pull it slowly, it kind of does this stretchy thing, but if you pull it quickly, it does this thing, and it's really neat stuff. So what I thought we would do is actually put some of this in the liquid nitrogen and see what happens to it. After a minute or two in the liquid nitrogen, the slime has also not only changed color into this lighter color, but it also has lost its flexibility. Oh, see, it shattered again. It's lost its flexibility and broken apart into these tinier pieces, like that. Definitely not slimy anymore. But we'll see what happens when it warms up. If you've been paying attention in chemistry class, you know about Charles' law. And Charles' law says that if there's a gas in a non-rigid container and you cool it down, its volume will decrease proportionally. So this goes in there and the liquid nitrogen cools it down, and I can feel it just sagging in there. So I'll flip it around a couple more times. And there it is, my sad looking balloon, but give it time. Hold that right like that, and as it warms back up, the temperature is going up and the volume is again increasing inside the balloon. So, how's that? Okay, so I'm really hoping that you can see this, but I have my ladle here filled with liquid nitrogen. You can see the fog rolling down, and right along the edge of the ladle on the top, you'll actually see some frost forming, and that is some water vapor from the atmosphere that is freezing. If you can also see, I'm getting these little drips, one just landed on my hand, of liquid that's falling off the bottom of the ladle. There is actually liquid oxygen. The atmosphere around us is about 21% oxygen, and some of that is actually liquefying underneath that ladle because the ladle is very cold. It's almost 200 degrees below zero, and oxygen liquefies at minus 183. So it's plenty cold enough to get little droplets of oxygen, and they're falling down and then they vaporize again when they warm up. Not often that you get to see liquid oxygen. My slime is back to room temperature and I was able to put it back together again, and it's definitely slimy again. Ew, ew. Nice and bendy again. Except we're not gonna be playing racquetball with this anytime soon. Speaking of liquefying things, because we can and why not, right now I'm liquefying some methane. And it is the primary component of natural gas. So I've actually got my tube here hooked up to my natural gas outlet over here that I would normally use to light Bunsen burners with. But right now I'm just sending it into my test tube, so hopefully when it gets under the surface, that, my friends, is what liquid methane looks like. Again, it's a clear liquid. You can kind of tell that it's cold. It's about minus 163 degrees. So pay attention in chemistry class. You also know that hydrocarbons are flammable. And even if this one is at minus 163 degrees, it's still flammable. So you know what that means. I'm out here in the hallway where it's a little bit safer, and we're gonna go ahead and light this part up top. That is the methane vaporizing and coming out of the top of the test tube. And with a little bit of luck, I'm gonna pour this on the ground and we'll see something very cool. I've never done this next thing either, but I was curious, since I could liquefy methane, if I could liquefy some other gases. I happen to have some containers of sulfur hexafluoride, which is an inert gas and contains sulfur and 6 fluorines around it. And it's a gas that's about 6 times as dense as air is, but I've never actually seen it in the liquid state, and I've never seen it in the solid state. Sulfur hexafluoride will turn into a liquid at around minus 51 degrees Celsius, and into a solid around minus 63. This is plenty cold to do that, but I don't know if I can get it to work properly. We're just gonna give it a shot. Do this, I'm just gonna open this up over my test tube and really slowly let some out. Let this go for a minute. Be right back. Check it out, we definitely have some solid sulfur hexafluoride in here, and a chunk just actually dropped down to the bottom. Let me wipe this off a little bit. You can see it a little better. All right, there we go. That's solid sulfur hexafluoride, and actually some of it has turned into a liquid. I can see it sloshing around there a tiny bit near the bottom of my test tube. I'm also seeing a little bit of a green color, which I was not expecting. The test tube I was using was actually clean, and so I'm not thinking that's an impurity or anything, but I'm definitely seeing sort of a greenish color down there. And that is just super fun. Sulfur hexafluoride, everybody. Another cool thing about sulfur hexafluoride is that because it's about 6 times more dense than regular air,
makes your voice sound really weird when you inhale it. Kind of like helium, except that it makes your voice go lower, which sounds really weird and actually feels a little weird also.
Last but not least, we're gonna take some liquid nitrogen, and using a funnel, we're gonna put it inside a soda bottle, and then we're gonna stopper the cap. But we're not gonna do this inside because gases tend to expand like 600 or 700 times their volume when they turn from a liquid into a gas. And so that's gonna cause the pressure to go way up, and if all goes according to plan, we should see something very cool. Going outside. I've never done this particular experiment with a soda bottle under a trash can, so I wasn't sure exactly how long it would take for the pressure to build up. So we had a few tense moments where we thought, is it going to go? Is it gonna explode? Is it not gonna explode? And we just had to wait for it. Ultimately, the bigger bottles, like this one, took about 5 minutes to build up the pressure that it needed in order to explode and shoot the trash can everywhere. Smaller bottles took a little bit less time. Don't try this at home. It's a little terrifying and definitely dangerous. So there you have it, some fun with my friends, the liquid nitrogen molecules. I hope you enjoyed it. We'll see you next time. Have a great day.